My name is Melissa Widhalm. So I am an applied climatologist by training who about 7 years ago turned project manager. And I now work in a university setting helping faculty and staff work on interdisciplinary projects that try to help different people integrate climate information into their decision making. So for a while I was focused more on agriculture and developing climate information for ag use throughout the Midwest. And now I'm working with the Purdue Climate Change Research Center, and I'll tell you a little bit about that in just a few minutes. So I really am honored and grateful to be able to come talk to you today about a topic that really is absolutely critical to our current day and our future water management, and that's our shifting climate. And more specifically, I want to spend a little time talking to you about some of the new work that we have coming out that's looking at the ways that our water and the climate will be changing. And I hope that it will be useful to you as you continue to work together to build a more resilient St. Joseph River Basin. But before we jump into talking about climate change, I want to zoom out for just a moment. I'd like to start a little bit further back than where we're sitting in the room right here today. So let's start here with this illustration of the world, two illustrations of the world with two colored dots on top. So the one on your left, that blue dot, or marble, or speck, that represents all of the water on Earth, so down to the depths of the ocean, in our ice caps, in our clouds, in our rivers, in our own bodies. All of the water, if you were to take it from the world, cram it all together, it would fill a marble that size. Right there.
Fresh water?
All water. All water. So it's an incredibly thin layer and fragile layer when we look at it like this. Now this one, this is what it would look like if we took all of our atmosphere, so from the ground up to the start of space, all around the world, we pushed it all together, stuffed it in a balloon, and put it down to sea level pressure. Our atmosphere would fit inside that pink balloon. So again, a very fragile layer. And we're all breathing and driving and flying and running our factories inside this pink balloon. All 7 billion of us. Now when we start to think about the atmosphere in this way, it's a lot easier to believe that we could be changing the concentration of gases in that bubble. And in fact, we have been. All of that flying and driving and running our factories has converted billions of tons of fossil fuels like coal and oil and natural gas into carbon dioxide. And as we continue to put carbon dioxide into the atmosphere, the concentration of that gas in that little pink balloon is rising. In fact, we know that our concentration of CO2 in the atmosphere had never been above this point until now. It's 300 parts per million. We're sitting right there. Now, since the start of the Industrial Revolution, when we really ramped up and have continued putting carbon dioxide into our atmosphere, we've increased the concentration of this gas by about 40%. If we zoom in to just about the last 130 years, and we overlay in white the concentration of carbon dioxide, and in blue, here, our global average temperature, we can see just how closely these two variables match one another, and just how rapidly we are changing the composition of our atmosphere. The rate of change that we are seeing is unprecedented, and it's significant. Now to think about this, to look at this in another way, what we're seeing here is for every year from 1880 to 2014, how much above or below average that year's temperature was compared to the 20th century average. So what we can see is that global temperatures are rapidly rising. And in fact, 9 of the 10 warmest years on record all have occurred since 2002. That 10th warmest was 1998. Now, when this graphic was developed, we had actually just reached our new record, the hottest year on record. It was 2014. That's when this was developed. But that was short-lived because in 2015, we achieved our warmest year on record. But that was short-lived because in 2016, we had our warmest year on record. Now, thankfully, I don't have to continue being a broken record. I can tell you that last year, in 2017, we came in third. Still very warm at about 1.5 degrees above the long-term average and keeping in line with our trend of this long-term warming. And also, last year represented our 41st year in a row with global temperatures above the long-term average. The chance of this streak happening, of 41 years in a row happening completely at random, in the absence of a changing climate, is 1 in a trillion. Now, while a few degrees of change might sound very small, it's actually not. Like our bodies, the Earth's temperature is highly stable, very stable. It moves up or down maybe a few tenths of a degree from year to year when you average it out over the course of a year around the whole globe. When we start talking about full degree or 2 or 3 of warming, this translates to significant and important changes in our local climate. And really, this goes beyond warming temperatures alone. As we warm, we are seeing alarming trends in key environmental indicators worldwide. So take, for example, Arctic sea ice, which has been warming and melting so rapidly that university scientists are telling us we can expect to start seeing ice-free summers as early as 2030. That's just 12 years away. And while these changes at the end of the Earth might seem very distant, they're absolutely critical. We have to understand that our world is an interconnected system. The Arctic sea ice is a major driver of the wind patterns all across the northern hemisphere. And those wind patterns, in turn, control the location and the intensity of the storm systems that come right through the St. Joseph River Basin. I'm sure many of us will remember the frigid winter of 2013 and 14 and how we were all talking about the polar vortex. It was all part of our vocabulary that year. That was an absolutely perfect example of the interconnectedness of our global climate system. But look, this isn't just something happening far away. We're not just seeing changes in these indicators in faraway places. We're observing changes happening right here at home, right here in Michigan, right here in Indiana. We see it in our precipitation record with about a 5 to 6 increase, 5 to 6 inch increase in annual rainfall over the last century in north central Indiana and in southwest Michigan. And more of that water is coming in heavy downpours. This is flooding our farm fields, washing away our soil. This is challenging our stormwater infrastructure. And we see these observed changes in our temperature record, with a warm season that's lengthened about 2 to 3 weeks over the last 50 years. If you're somebody who suffers from allergies, you notice this. This is changing the seasonal water demands in our natural systems and in our human-built systems. And we see these changes with warming in our overnight temperatures and with fewer and fewer cold events over the last few decades. This puts us at significant risk for insects and pests that can be really harmful to human health. They can devastate agricultural lands, they can devastate forests. When we're warming these winter temperatures, it also changes our snowfall, our snowpack. It changes our flood risk. Our climate is changing. And it's going to continue to change into the foreseeable future. And so we need to know, how will these changes globally affect me locally? How can we put these global changes into a local perspective? And that's exactly the question that Dr. Jeffrey Dukes asked a few years ago when he took over as director of the Purdue Climate Change Research Center. He said, what will climate change mean for Indiana? Sorry, Michigan, we're based in Indiana. And what will it, and how can the Purdue Climate Change Research Center help answer these questions? So the PCCRC, as we call ourselves, we are a faculty-led center at Purdue University. We have about 80 faculty working across a number of topic areas. We represent about 22 departments on campus. So we're working on a broad range of subjects related to our changing climate. And not just in Indiana, but also throughout the region and throughout the world. Our faculty are involved in research, as well as education and outreach. And we strive to be a high-quality source of scientific information for decision makers in our state and beyond. And so, this isn't actually the first time our center has asked the question, what does climate change mean for us? About a decade ago, we had one of our U.S. senators in Indiana, Senator Lugar, reach out to the center and say, hey, I know I'm going to be voting on some climate change legislation. I need to know what climate change means for Indiana. Oh yeah, and I need to know in about 3 weeks. Okay, so in about 3 weeks' time, we expanded out across our network on campus, and we were able to come up with this report, The Impacts of Climate Change for the State of Indiana. And since then, there's been a tremendous amount of research that is happening nationally, regionally. There's been a lot of reports, a lot of work. But in terms of our state and local information, we're still relying on this decades-old document. So a few years ago, we decided at the PCCRC that it was time to update this effort. But we didn't want to do it in 22 days. We wanted it to be a lot more comprehensive. And we wanted it to involve other experts, not just those at Purdue. And so now, with about 100 collaborators from across Indiana on board, we are working on what's called the Indiana Climate Change Impacts Assessment, with the goal of trying to understand, what does climate change mean for our state and local interests? And so one of the major outputs from this effort is a series of individual reports, non-technical reports, looking at climate change impacts. So I have those listed up here. We started releasing these reports just a couple of months ago. And so if you go to indianaclimate.org, you can find our climate report, you can find our health report. And I'm really excited to say that in just a few days, you'll be able to find 2 more reports coming out of this group. And we'll have additional ones released later this year and into 2019 as well. And so with the remaining time that I have here with you this afternoon, or I guess it's still morning, I want to talk about some of the main results that are coming out of this assessment, and more specifically focus on the key ways that our climate averages and extremes and seasonality will be changing and what that means for water resource management and planning. Now, I completely recognize that the St. Joseph River Basin covers portions of both Indiana and Michigan. And so as appropriate, I'll bring in some other resources to paint a better picture of that local perspective for everyone. But it really is important to keep in mind that, a lot of the changes we're talking about, it's very similar no matter which side of the border you're on. There's really not that much difference in those projections. All right, so let's start with temperature, and specifically our statewide average temperature. And this is for Indiana. And so what we're looking at here, this orange line, this bouncing around orange line, that is showing us for each year, going back to about 1900, how much above or below average the annual temperature was that year. So similar to what we were looking at the global scale, but this is for the state. And the black line is overlaying that long-term trend. And so based on this trend, we already know that Indiana's temperature has warmed about 1 degree Fahrenheit over this last century, and that our warming has been accelerating since about the 1950s. Now, if we move to the right half of this graphic, what we're showing are projections of our average temperature. So for the Indiana assessment, we took 10 climate models to try to look at the future. And so a lot of what I'm talking about is an average of those 10 models. But even though I'm talking about the average, it's always important to keep in mind there's a range of outcomes that are possible, but with some very distinct patterns that emerge. So when we're looking at the right side of this graphic, this red area here, that red area is showing us the projected change in temperature, assuming we make no changes at all to what we're doing, to how we're powering our world, growing our food, transporting our goods. This is the path we are actually on right now. It's not the extremist or the alarmist path. This is where we are today. This is what happens if we do nothing. Contrast that with the green area here. The green area is showing the projected change in temperature if we were to take some pretty drastic steps to make significant and important cuts to the emissions going into our atmosphere. So based on the best available models that our scientists have, they have concluded that Indiana's average temperature by the end of this century will warm about 5 to 10 degrees Fahrenheit, depending on how much of that heat-trapping gas gets into our atmosphere. That is a tremendous amount of warming. We can do the same thing for Michigan. We can look at that, and it shows pretty much a similar trend historically and in the future as Indiana, if not slightly more extreme. There's actually been more warming in Michigan, and the projections show slightly higher amounts of warming by the end of the century. Now, if we only look at our annual average, we're only getting a portion of this story. Our picture becomes much more complete if we start thinking about these changes seasonally and also about the occurrence of extremes. And so, thinking about temperature as an example, if we want to look at this in a different way, what we're showing here is our average summer conditions. So now we're looking at that summer season, that June, July, August. And by mid-century, the projections are showing that our average summer conditions would be more like that of the average summer conditions you would find in western Tennessee or central Arkansas. And when I say mid-century, I'm talking about this 30-year average period from 2041 to 2070. If we want to look at winter, we can do that as well. And by mid-century, under that high emission scenario, the scenario we are currently on the path for, our winter average conditions look more like that of states that are pretty far to the east of here. I'm only showing you Indiana, but Michigan takes a similar path with it warming and drying in the summer and warming and wetting in the winter. Now what about extremes? For this, we can think about days when our temperature gets to 90 degrees. So we don't have to be talking about those ridiculous 100-degree days that almost never happen around here. We can look at an extreme of 90. And for this, we're looking at an average, a countywide average for Elkhart County, Indiana. And so if we look at our historical data going back about a century, we can tell that If you average it out each year, if you look at how many 90-degree days you had in each year, some years will be more, some years will be less, you average it out, and we see that it happens about 14 times a year when we hit 90 or above. So it's not unusual. It happens quite a bit. But even still, we all know how uncomfortable a 90-degree day is, and frankly, how dangerous a 90-degree day is if you work outside or if you don't have access to air conditioning. When the temperature gets this warm, we start to see declines in our air quality. If you're somebody with asthma or heart disease or another chronic condition, that's not good. That can be deadly. When the mercury rises to this level, we also see skyrocketing demands in our water, both in human and natural systems. So we don't have to be talking about very extreme high temperatures to be talking about real impacts on our life, real impacts on real people, you and I. A 90-degree day will do it. So in the past, we'd see this about 14 times a year. What are our projections showing us for mid-century? It's showing us 60 days per year of reaching 90 degrees or above in Elkhart County, Indiana. 60 days. Just as we'll be seeing an increase in those heating events, we'll be seeing decreases in cooling events. So fewer days where our temperature is dropping below the freezing mark, and a warming of that lowest temperature of the year. So here I'm showing on the left, this is the past. So this is again that average. If you look at every year, what's the lowest temperature, and then you average it out. In northern Indiana, you get about -9. Some years, like 2018, it's going to be significantly lower. Some years it's not even going to come close to that. When we average it out, that's about the baseline we're looking at. If we project forward into mid-century, we're talking about -2 degrees Fahrenheit, so a significant and consistent warming throughout the state. If you're somebody like me, when I first see this, I'm thinking, great, I personally don't really like the cold. I'm a Midwesterner, I was born and raised here, been here my whole life. You think I'd get used to it? And it'll certainly save us some money on our heating bills. But we have to know this comes with significant and real consequences, especially with insect pests. And as I'll talk about in a few minutes, when we're warming our winter temperatures, we're changing our snowfall, we're changing our snowpack, we're changing our flood potential. This comes with serious consequences. Just as temperature will be changing, so too are precipitation patterns projected to change. So our scientists are telling us we can expect annually in Indiana about an 8% increase in our rainfall. Maybe 8% doesn't sound like too big of a deal. We're a water plentiful area. We can deal with some water. But really a different story emerges if we break this out by season. We're talking about significant increases in our rainfall in winter and spring. This is a time of year we don't need the water. We already have the water. This is going to create a lot of pressure on our flood management capabilities, our stormwater infrastructure. And the models are in extremely high agreement with this, with our winter cold season and our spring season getting wetter. On the flip side, when we look at summer and fall, there's actually a little less agreement in the models. Some of those 10 models are showing some slight increases, some are showing some slight decreases. And when you average it out across the 10, we're looking at some modest declines at a time of year when we actually want the water, when we need it for agriculture, when we need it for wildlife, when we need it for drinking water. You pair that with increasing temperatures and more evaporation, and this will lead to significant water stress and maybe even water shortages. In addition to seeing increase in the amount of rain, Our scientists are telling us that we should be expecting an increase in our heavy downpours. More rain coming in heavy downpours, more heavy downpours happening frequently. This is a trend we have already observed over the last 50 years. This is already going on, and it's projected to continue and intensify. This will give us problems for soil erosion, for flood control, for water quality. Now, a natural question when I tell you that our temperatures are warming and we're getting more precipitation in the winter, well, is it coming as rain or is this coming as snow, right? Because this really matters. This makes a difference in our snow removal budget. It makes a difference for soil temperatures. It makes a difference for flooding. So what I'm showing you here is a map that is looking at how much of our cold season, so we're looking at November to March, how much of that precipitation, what fraction, comes as rain versus snow. So here, 0 would be all rain. If we went up to 100, 100 would be all snow. So based on the past, we know that about 30 to 40% of our precipitation in the cold season in northern Indiana falls as snow. When we look at how this projection is for mid-century, we're seeing that come down to about 15 to 20% of our cold season precipitation falling as snow. And this directly translates to a reduction in the number of days that have snow covering the ground. Statewide for Indiana, we're looking at about a 40% decline. Now, all of these changes in our temperature and in our precipitation patterns, they're going to lead to changes in our hydrology, and they're going to require that we adopt new practices, changing practices to deal with all of these impacts. Now, this is looking at north central Indiana, so not just the county. This is like a 10-county area. And we're showing that our scientists are telling us that we can expect to see about a 7% increase annually in the runoff in this region. So that's the amount of water going into our rivers and streams. And this includes both our surface runoff as well as our water coming from the tile drains. If you're interested in just the tile drains, we can focus in on that. And we find that there's significant increases annually with the majority of this coming in the winter and spring. More flow out of those tile drains, bringing all sorts of things into our waterways, giving us all sorts of challenges in our management and in our planning. Now, just like with rainfall, if we break this down by season, a slightly different picture will emerge. We'll get a more complete picture of what we're looking at. And so again, we're talking about more increases in the winter and spring, no change to some declines in the summer and fall. Shifting these patterns of runoff will have serious implications for our water quality. So we're talking about the water's purity, the amount of chemicals in the water, the type of chemicals, the temperature of the water, the amount of oxygen in the water. Water's purity, or the water's quality, can really be affected through both high runoff and low runoff. And when water is of insufficient quality, we can see some serious impacts. We see impacts in our environment with fish kills. Or you can see a reduction in your power plant capabilities, your power production capabilities. If the water temperature is too high and you can't take it out of that river to use it in a cooling tower. That actually happened during the 2012 drought in Indiana. You could lose your drinking water like this. This is what a harmful algal bloom looks like at a water supply intake off of Lake Erie. These are the types of consequences we face as our climate and as our water affects our water quality. Sorry to show you that before lunch. Okay, let's look at just one more metric, and that's stream flow. And for this, we're going to look at some work from one of our partners, Alan Hamlet at the University of Notre Dame. And this work is specific to the St. Joseph River Basin. And so what his team has found is that in the past, so going back through time, we see increasing trends in both the daily average stream flow and in the peak annual stream flow. These have been increasing over time, and they project that these changes, these trends, will continue and will intensify. So here we're looking at the peak annual stream flow. So this is at the Niles gauge, the USGS gauge in Niles. And so for each year, we're going back to 1930, we're looking at how high was the peak flow of the year, highest flow of that year. We're plotting it out over time. And what they found was that over time, there's an increasing trend. The highest flow is getting higher. They also found, and this is really interesting, a difference in the average, a difference in the mean, if you break up the first part of the record compared to the second part of the record. That's what these colors are showing us. When we're shifting, when our peak annual stream flow is changing, that makes it extremely difficult to use historical data to plan for the future. You are aiming at a moving target. They also looked at the change in the 100-year flood. So this graphic is a little bit complicated. Bear with me while I walk us through. So what they looked at, they used their computer models to project forward the change in the magnitude, the size of the 100-year flood. So that's the flood that's so severe that there's only a 1% chance of it happening in any given year. And so here across the bottom, we're looking at the 30-year period surrounding the 2020s, the 2050s, and the 2080s. And as you go vertically, these dots, the light colored dots, that's showing you the result from each of the individual models. And then the darker dot, that's an average for all of those models for that time. And then we're looking at the low emissions and the high emissions. So if we focus in here at mid-century, like we've been talking about, for the high emission scenario, that's here in the red, they're projecting a 35% increase in the magnitude of our 100-year flood. So that biggest flood is getting bigger. Flooding is happening more frequently. This is the future we need to be dealing with. When you bring it out to the 2080s, it jumps up to about 45% increase in the size, the magnitude of the 100-year flood compared to what we see today. So I realize I've given you a lot of information. There's a lot to think about. I will give you the 45-second recap. Our climate is warming. It is wetting. And the best available climate models and information we have is telling us these trends will continue and intensify. We are going to be challenged by an increase in extreme heat, by increases in rainfall. And if we want to effectively manage the risks that come along with these changes in our climate and our water and that ripple through our environment, we have to be thinking about the seasonal changes in addition to the annual trends. And remember, where we end up depends on the choices we make. We need to get serious as a society about reducing the amount of heat-trapping gases in our atmosphere if we want to avoid the most severe consequences to our water resources and to our infrastructure by the end of this century. These are real differences, and I'll give you some examples. So if we do nothing, if we stay on the path we're on, that red emissions path, if you think back to one of those early slides, based on a report from 2015 from the U.S. Environmental Protection Agency, we're looking at 190,000 inland bridges in the U.S. that will be structurally vulnerable to climate change by the end of this century. If we look at our region right here, we're talking about 37% of our bridges being at risk and requiring costly maintenance and repairs to remain usable. We can contrast this with just 9% of bridges being at risk in the low emission scenario. So making changes today will have an impact in the long run. They also looked at water quality. So they looked at the water quality outcomes for these two scenarios: do nothing or take some pretty aggressive actions to reduce those emissions. What they found, these are US numbers, averaged across the whole US. What they found was that the cost of dealing with poor water quality in the low emission scenario was 82% less than the cost of dealing with poor water quality in the high emission scenario. And so if you think about that in terms of real dollars and cents, that's about $3 billion in avoided costs by getting off this high emissions path. Now, the unfortunate reality is that even if we were to drastically reduce our emissions right here, right now, today, immediately, we will still be seeing some of these changes. You'll remember this graphic from earlier. If we focus in on just the next few decades, the projections are virtually the same, no matter which emissions path you're on. And that's because we already have a certain amount of warming baked into the system, based on the amount of heat-trapping gases already there. So what this is telling us is that communities need to be acknowledging this fixed level of change that we are in for, and we need to be preparing for them. We need to be adapting our systems. How can we build resilience in our communities to the local changes we know are already happening and that are coming into the near future? That's the key question. And actually, this is the point where I want to toss it over to Matt and bring him up here and get him involved, because I'm a climatologist by training. I was fascinated sitting through the lightning round, or whatever you called it there, to learn about the different options that people are taking to reduce stormwater runoff, to get some of those combined sewer overflows out of our waterways. I'm not experienced in those things, but I know a lot of you are. There are a lot of strategies out there that communities and projects could be implementing to help us deal with the changes we already have. And I think that's what Matt would like us to talk a little bit about with our remaining time.
Thanks, Melissa. First, can we get a round of applause for